Okay. Thank you. So first of all, I'd like to thank the organizers for inviting me to give these talks. Now, Subhro had given a specific task to me, which is to review old work on anomalies. So what I'm going to talk about today will be more than 50 years old. Probably most of the audience was not even born at that time. Their parents probably were in the kindergarten. So you have to bear with me, and hopefully in the later lectures you will learn more modern material. I also apologize for using the slides, but my experience in this room is that it's very hard to see the blackboard from behind. Okay, but I'll try to go slow. And anytime you have any questions or if you want me to slow down, please don't hesitate to speak out. So the lectures will be on anomalies in quantum field theories. So let me begin by saying what anomalies are. So these you can think of as symmetries of classical theory. When you write a quantum field theory, you first start writing a classical field theory, classical action. So anomalies are symmetries of classical theory, but these are destroyed in the quantum theory. And in this talk, I'll be taking the ultraviolet viewpoint. And that is the fact that quantum field theories have ultraviolet divergence. And as a result, they need regularization and then renormalization. Okay, so these are the two things which extract finite result from divergent results in a quantum field theory. And anomalous symmetries are not symmetries of the regulated theory. Okay, and so essentially it's the ultraviolet divergence of the theory that is responsible for breaking of this symmetry. Now here I should add that this is a necessary condition, but not a sufficient condition. Okay, there are examples where there is no regulator which preserves the symmetries of the classical theory. Nevertheless, that symmetry is non-anomalous. And we will see some example later. But one standard example of this is the standard model of particle physics, okay, that describes all the elementary constituents of matter. Here, the gauge symmetry that we have in the standard model of particle physics doesn't have a regulator, okay, which preserves it. Nevertheless, the symmetry is non-anomalous. Okay, and we will see later how this could happen. Are there any questions? Yes, yes.
Of course, you gave examples in quantum field theory, but in elementary quantum mechanics, are there examples of anomalies? In other words, you need to have infinite dimensional spaces and or infinitely many degrees of freedom to have anomalies.
Yeah, so I agree. Yeah. Whenever you need, some regulator, you have anomalies.
Sir, last but the case line I am not able to understand.
This one?
So kindly.
Yeah, so this is probably not easy to understand at this stage, but later on when I give examples, right, of theories which have no regulator, okay, nevertheless they're non-anomalous, that will become clear. Okay, so this is just a statement for now. Okay, and we'll see later. Okay, so most of this lecture, at least, I'll focus on massless Dirac fermion in 1+1 dimensions, okay, because that can be used to illustrate the role of anomalies, and it's a simple example. Okay, calculations can be done explicitly even during a lecture. So we'll start with that. Okay, and let's for a few minutes keep non-zero mass, okay, and later we'll set it to 0. So we'll start with Dirac equation in general dimensions, okay, and the reason I am doing this is because eventually we'll also be discussing 3+1 dimensions. So this is the form of the Dirac equation in general dimensions, where m is the mass and the gamma mu's are the usual gamma matrices, which satisfy the following relations. So in my convention, gamma 0 is Hermitian, gamma I for I larger than 0, which are the space directions, where I is just 1 in 1+1 dimension and 1, 2, 3 in 3+1 dimensions. They are anti-Hermitian. And the gamma matrices satisfy an anti-commutational relation of this kind, where eta in my convention is that this is a Minkowski metric. It's a diagonal matrix with first entry, the 0, 0 entry being -1, and the rest of the entries being 1. So in particular, you can see that if you set mu and nu equal to 0, okay, then gamma 0 square, okay, this left hand side is 2 gamma 0 square, right hand side, sorry, left hand side is 2 gamma 0 square, right hand side is -2 times -1, that's 2. So that basically says the gamma 0 square is 1, and similarly gamma I square is -1. And I'll be using the summation convention. So whenever an index is repeated, it's understood that it's summed over all the possible values. Okay, so in 1 plus 1 dimension, the mu is summed over from over 0 and 1, and in 3 plus 1 dimension, it will be summed over 0, 1, 2, and 3. So this is a Dirac equation, but we can also derive it from an action, okay, which is given here, where psi bar is the psi dagger times gamma 0. And psi is a column vector. Okay, it's a 2-dimensional column vector in 1 plus 1 dimension and a 4-dimensional column vector in 3 plus 1 dimension. Now, from this action, we can derive the fermion propagator, okay, and I'll be working in the momentum space. Okay. So in the momentum space, this derivative becomes I times p mu, okay, if p is the momentum. And so this gives rise to a propagator, which is given here, where p slash is a notation that I have introduced, okay, which is minus eta mu nu gamma mu p nu. This minus sign again is just a convention, but with this minus sign, okay, the kinetic term you can write as p slash minus m, and hence the propagator is the inverse of that, which is given here. And this can also be rewritten in this form, okay, where p square is eta mu nu p mu p nu. So this is valid in both 1 plus 1 dimension and 2 plus 1 and 3 plus 1 dimension. In fact, in any dimensions, okay, up to this point, nothing is dimension dependent. If we focus on d equal to 2, okay, then we introduce this chirality operator gamma 5, okay, which is gamma 0, gamma 1. Okay. Now the reason that I have called it gamma 5, even though there is no gamma 2, gamma 3, and gamma 2 and gamma 3 in 2 dimensions, is because eventually we will be working also in 4 dimensions. So just not to confuse you with the gamma matrices that we'll be having there, we'll call this product as gamma 5. And it follows from this that gamma 5 square is 1. There are some other useful relations. If you take the product of 2 gamma matrices, this is specific to 2 dimensions again. It's given as a sum of 2 terms like this, where epsilon mu nu is an antisymmetric matrix with epsilon 0, 1, 1 and epsilon 1, 0, minus 1. And another useful relation is that if you take the product of gamma 5 and gamma mu, it's given by minus epsilon mu nu gamma nu. Okay, but these relations are specific to 2 dimensions. Are there any questions on this? Okay. So now, if you look at the free theory, okay, which the action I wrote here, okay, then for m equal to 0, okay, one can easily convince oneself that this has 2 symmetries. One is simple phase transformation of psi. The other one is a phase transformation, but weighted by this factor of gamma 5. This one is very easy to see, right? Because you just have psi picking up a factor of e to the I alpha, psi bar picking up a factor of e to the minus I alpha, and they just cancel. If you have I beta gamma 5, okay, then this picks up a I beta gamma 5, and then you have to pass it through for m equal to 0, right? Gamma 5 passes through gamma mu, picks up a minus sign, but then there is also a gamma 0 over here, so that gives another minus sign. So again, you end up with e to the minus I beta gamma 5 from psi bar and e to the I beta gamma 5 from psi, and then they cancel. But this requires that mass should be 0. And then there are corresponding northern currents, okay, which I have introduced here, JMU and JMU5. And this, in fact, you can write as minus epsilon mu rho J rho, because you have this relation over here. Okay, this will not be too important for us, but let's just mention this here anyway. And one can explicitly check that if you calculate the divergence of J mu, okay, here using the equations of motion that I have written here, okay, there is a similar equation for psi bar, which follows from, of course, this one, right, and all the relations that I have written here. Then the divergence of J is 0 and the divergence of J mu 5 is proportional to M, but again when you say M equal to 0, this becomes 0. So essentially the point is that this is not conserved when M is non-zero, but it is conserved when M is 0. And then there is another relation that we'll be needing, and that is that you can try to use the Poisson bracket. Okay, so this is the Poisson bracket that you get from the action over here. Right? You can see the Poisson bracket. So you have defined the canonically conjugate momentum by taking the derivative of the Lagrangian with respect to del 0 psi. That gives you I gamma 0, and psi bar gamma 0 will be psi dagger again. Okay, so the conjugate momentum to psi is essentially I psi dagger. And using that, one can check that these Poisson brackets are true. Maybe I have missed out some factors of I over here. I should say that I have tried to fix all the factors of I, but certainly I cannot guarantee that they are all correct. Right? So I think there are some I's missing from these relations. Okay, but it will not be too important for what I'm going to say. So naively, okay, if you look at all these relations and see what we expect in the quantum theory, what we expect is that in the quantum theory, these will be conserved by correspondence principle, J mu and J mu 5, and then the vanishing of these Poisson brackets will lead to the relation that J mu and J mu 5 will commute in the quantum theory. Okay, so we can start from here and then use the Poisson brackets, use the standard rules to calculate the Poisson bracket between this and this, and that you can use that computation shows that this is 0, okay, and hence once this is 0, then the corresponding quantum relation, if it assuming that it goes through in the standard way, will be that this should be 0 in the quantum theory. And what we will see eventually that we cannot preserve all three relations in the quantum theory, right? We cannot have J mu conserved, J mu 5 conserved, and the Poisson bracket satisfying the commutator bracket, okay, following what we get from the Poisson bracket. Okay, and this is where the role of anomaly will come in. Yes.
Can you use the microphone?
I think somebody has to use the microphone.
So I was asking, what's the dimension of this gamma matrices? Is there?
Yes.
So are they 2 dimension or they can be any dimension?
In general, they can be any dimension, but in 1 plus 1 dimension, the gamma matrices can be taken to be 2 dimensional. Right? So just Pauli matrices will be done.
Because if their dimension is greater than 2, they can be more conserved, correct? Should I expect?
Yeah, we are thinking of here as a 1 Dirac fermion. Right? For 1 Dirac fermion, we can represent the gamma matrices as a 2 by 2 matrix. Yes.
If I had a chiral mass, how would the current conservation relations be changed?
If you had a
Chiral mass.
If you had a chiral mass, then the gamma mu, the psi bar gamma mu psi will not be conserved. So no, I think psi bar gamma mu psi will always be conserved. Yeah. So even if you have a chiral mass, it's the same. Right? There will be some extra gamma 5 maybe in this relation. Right? You are thinking of psi bar gamma 5, psi bar m times psi bar gamma 5 psi. That's the kind of mass you are talking about, right? Yeah, I think there will be some extra gamma 5 that will be inserted, or maybe this gamma 5 will not be there, right, in the second one.
So I think maybe I'm being naive, but the symmetry between chiral mass and ordinary mass is just an illusion.
Yeah. Meaning the chiral symmetry, okay, we'll see the chiral symmetry and ordinary symmetry can be exchanged, okay, by in 2 dimensions, but not the chiral mass and ordinary mass. Yeah, so you can work out what happens if you have a psi bar gamma 5 psi coupling. In fact, I think effectively you can, if you think in terms of left and right moving fermions, right? Then in one case you have psi bar L psi L plus psi bar R psi R. In the other case you have psi bar L psi L minus psi bar R psi R. That's and then you can work out what are transformations, what symmetry will be preserved. I think by chiral mass he meant the gamma 5 inside it. That in the expression over here, put a gamma 5, m gamma 5. I think that's what we meant, right? Yes.
One question, just to ask, what is the difference between the ordinary symmetry and ideal?
Chiral symmetry has a gamma 5. That's all, right? That it involves a gamma 5 in the transformation law. Yeah, so this is what we call a chiral symmetry. Or this is an ordinary symmetry. This is an example of an ordinary symmetry, right? Which has no gamma 5. Any other question? Okay. So now let's look at massless fermions. So if you believe that all the classical results that we got, okay, lifts to quantum results, then you would expect that we should have the usual J mu current conserved, J mu 5 current conserved, and this commutator should vanish. So now let's calculate this means the derivative with respect to x mu, del del x mu. Let's calculate using path integral, and this is what also appears in various perturbation theories. Now, this operator, time ordering involves a step function, right? If you recall the definition of time ordering, there will be a theta of x0 minus y0, for which this is the ordering, and there will be theta of y0 minus x0, in which case J nu will come before J mu 5. Okay, that's time ordering. And when you apply the del del x0 on the theta function, del del x1 doesn't do anything, right? It just goes through. Del del x0 on the theta function will give a delta function, and it will become a commutator between these two at equal time. Okay, because delta function will set x0 and y0 to be equal, that means the corresponding times are equal, and you will get a commutator. But because the commutator is 0, we can actually take the derivative inside the time ordering, and you arrive at this, and then you use the fact that J mu 5 is supposed to be conserved to conclude that this should be 0. And similarly, you can also take the derivative with respect to del del y nu, okay, and again because of this, you expect that that should also give you 0. And as I already said, we will show that in quantum theory is not compatible with this relation and the corresponding relation with this relation and the corresponding relation where del del y nu acts on J nu y. Okay, so both J mu 5 and J nu cannot be conserved simultaneously, and at the same time this commutator will not vanish. Right? So either this commutator doesn't vanish or one of these conservation laws have to be given up. Right? That's what we'll try to show. So just to simplify notation, I'll use this shorthand, okay, which is often used in quantum field theory, that will denote this expectation value of J mu 5, J nu y, right, without these vacuum expectation value and the time ordering. But it should be understood that what I mean by this is always this. Contact term? Well, Poisson bracket doesn't have a contact term, right? So what I'm saying is, if we lift this commutator bracket, Poisson bracket to the commutator bracket, then there is a contact term, right? Because the classical theory doesn't have any contact term. You can calculate this Poisson bracket, okay, and this is what we get.
Or charged under each other. That's
Pardon? Yeah, these are not charged. Yeah, these are not charged. Right? J mu 5 doesn't carry any J mu charge. Okay, so now it will be useful to work in the momentum space, okay, because the Feynman diagrams are best done in the momentum space. So in the momentum space, we will define the Fourier transform of J mu x, J nu y, okay, in this way. And because of the translation invariance, we expect this to be a function of x minus y, okay, and that translates to momentum conservation. Okay, so this object, okay, is a function of a single momentum, okay, p, and whatever that function is, we will call it s mu nu. Okay, and then there is this momentum conserving delta function which is given here. Okay, so this essentially is a definition of what we mean by s mu nu. And then these relations, okay, this relation, for example, in the momentum space translates to p mu s mu nu equal to 0, and this relation, okay, once you convert to momentum space, it becomes p nu s mu nu equal to 0. So you want to check if both these relations can be true, and as I said, we will show that it cannot be true. Both these relations cannot be true. Okay. And since these relations were derived using the current conservation laws and this commutator, okay, one of these must fail. Any question? Yeah. Oh, in the presence of mass, this is not true anymore, right? Because the symmetry is there only for massless particle. If you look at the previous expression, right, del mu j mu 5 had a mass term proportional to m. So only if m equal to 0 that this is conserved. Okay, so now we want to compute the Feynman diagram for computing this, right? So you need the Feynman diagram for S mu nu. And here is the Feynman diagram. Okay, so you have inserted J mu 5 at this vertex, J nu at this vertex, and K is the loop momentum that is flowing through. So the way I have organized, the momentum P is flowing out from here, and momentum minus P is flowing out from here. So this is the loop momentum, and then we can use the standard Feynman rules to write down the expression for this S mu nu. This will have a momentum, the loop momentum integral, and then there is a trace of gamma 5 gamma mu, and then you work opposite the arrow, right? So this arrow refers to also both the momentum as well as the lines. You work opposite the arrow, so gamma 5 gamma mu I over k slash, and gamma nu from here I over k slash minus p slash, and then you take a trace because it's a closed loop. And now when you examine this, you see that this is a logarithmical divergent integral, okay, just by naive power counting, because for large k, you see that d2k has two powers of k, okay, 2k integrals, and we have two powers of k in the denominator, one from here, one from here. Okay, so this integral is logarithmical divergent. And we want these relations, right? We want to see if these relations are true or not. So first, I'll give a formal proof that these relations are true. But this will be formal, it will not be actually correct. Okay, and I'll also explain why this proof is not correct. So what is a formal proof? Okay, let's just calculate P nu S mu nu, okay, which is trying to test the second relation over here. So P nu, okay, will directly contract to gamma nu, and P nu gamma nu is minus P slash. Okay, so that I replace in this gamma nu by minus P slash, so that is the minus sign. Then this P slash I can write, or the minus P slash I can write as a difference between K slash minus P slash and K slash, which is here. And now you see that this term, okay, this cancels this. That gives you, the I square is minus 1, right? That gives you this minus 1 over K slash, because you are only left with 1 over K slash here. And then this one cancels this, okay? So you are left with 1 over K slash minus P slash. Okay, so this is what you get by applying P nu S mu. And now you say that because we are integrating over K, we can shift momentum, right? Let's just define K minus P as K, okay, or as K prime. So you'll get d2K prime 1 over K prime slash minus d2K 1 over K slash, and then of course K and K prime are just in dummy variables, integration variables. The nuclear K prime, replace K prime label by K, and you get 1 over k slash minus 1 over k slash, that is 0. So if you are allowed to shift the momentum k to k plus p, then this object is indeed 0. But the caution that I want to add here is that such manipulations can be dangerous in linearly divergent integrals, right? Here you see that each of these terms is linearly divergent, and shifting the integration variable in a linearly divergent integral can often lead to inconsistencies, okay, or wrong answer. Okay, and we'll in the next slide I'll explain. I'll just give an example of how linearly divergent integrals can give strange answer if you are allowed to shift variables. Any question on this? So this is the formal proof that P nu S mu nu is 0, right? If you are allowed to shift momentum, you can show that P nu S mu nu is 0. Now I'll do the same thing for P mu S mu nu. So again, this is the expression for S mu nu. And now what I have done here is, let's see what I have done here. I have taken the I over this 1 over k slash minus p slash. So first of all, I square is minus 1. Okay, that I have taken out. And then 1 over k slash minus p slash, because of the cyclicity of the gamma matrix, I have brought to the other side. Okay, 1 over k slash minus p slash. Sorry, here I have not taken out I yet. Okay, I is there. And then we have a 1 over k slash minus p slash times gamma 5, and then using the commutative fact that gamma 5 anti-commutes with the gamma slash of all the gamma mu's, I can rearrange the order, gamma 5 first and then I over k slash minus p slash, and in that process we get an extra minus sign. Okay, so this minus sign is because I have rearranged gamma 5 with I over k slash minus p slash. Okay, and I am allowed to bring it here because there is a trace, and inside the trace I can use cyclic permutation. Once I have this form, I can play the same game again. So P mu S mu nu, this time I am contracting the mu index with P mu. And I write this P mu gamma mu factor, okay, which is minus P slash as k slash minus k slash minus P slash. The extra minus sign has killed this minus sign. And now again, I cancel, in the first term, I cancel this k slash, in the second term, I cancel this. Okay, and I am left with the expression that it's given by a difference similar to what we had earlier. And in this process, if I am allowed to shift k by p, okay, again we see that these integrals are identical and they give you 0. Is this clear? And here I should just say that in these manipulations, in this part of the manipulation, here, even if you had an m, it wouldn't have mattered, right? Because this would have k slash minus m, this will be k slash minus p slash minus m. Okay, so you could just add minus m in both, okay, and they will still cancel. But for this manipulation, okay, I had to take this gamma 5 through this I over k slash minus p slash. So it was important that it was just k slash minus p slash and not k slash minus p slash minus m. So the masslessness is important in verifying P mu S mu nu equal to 0, which is of course not surprising because this conservation law holds only for massless theories. So again, this manipulation is dangerous, and here I have given an example how a linearly divergent integral can lead to problem if you try to just naively shift the variables. So imagine that you have an integral from 0 to infinity dx. We declare x is y minus c, right? So I write it as integral c to infinity dy. And then I can write it as from integral 0 to infinity dy minus c, that's the integral from 0 to c, I have subtracted out. And now if you rename variable y as x, right, I guess integral 0 to infinity dx minus c. So if you have a linearly divergent integral, you can essentially make it anything that you like. Okay, so one shouldn't manipulate linearly divergent integrals, okay, by shifting. And in fact, what we'll do is to try to ensure that at no stage we encounter linearly divergent integrals for this manipulation. Are there questions? So let me again summarize what I have said so far. So essentially what I have said is that it is possible to give a formal proof of both these relations, this relation as well as the other relation that we wrote, this one. But we should be wary of these formal proofs, because in actual practice this will not be the case. And that's the source of anomalies. Okay, so if there are no questions so far, I'll start with the actual calculation. Okay, where we will not try to shift integrals in a linearly divergent integral, shift to integration variables. So this is our starting point for S mu. Now, if you look at this S mu, okay, we see that this is a logarithmical divergent integral. I have already said two momentum integrals and two parts of momentum in the denominator. And this basically says that this is ultraviolet divergent, but the ultraviolet divergent part is P independent, right? Because the divergence comes when the K becomes very large, and when K becomes very large, this P slash, the P can be ignored compared to K. Right? Another way of saying this is if we just expand this in parts of P over K, right, then the leading term is divergent when it's I over K slash I over K slash. The next term will have P slash over K slash. Okay, and that already has three parts in the momentum in the denominator, which makes it ultraviolet finite. So a divergent part we expect will be P independent. And we will do the calculation explicitly later, and we will see that indeed the divergent part is P independent. Now let's look at this expression. So it's a tensor, right? And we can try to write down the most general structure of S mu nu that is consistent with two-dimensional Lorentz invariance. And here, of course, I am assuming that the Lorentz symmetry is unbroken in this analysis, right? We'll have to, we basically have to do everything that in our power to make sure the Lorentz invariance is not broken. Sometimes that we may not succeed, okay, but in this case, we will succeed, right? We can get Lorentz invariant result. So here is the structure, okay, I have written down all the terms, okay, that we could possibly write down. In fact, the last term is extra, okay, it's not absolutely straightforward to see, but this tensor structure that you see here in 1 plus 1 dimension is actually a linear combination of these two tensor structures, right? So you don't really need this, we don't need this to write down the most general expansion. So we could just stop at F4. And here, because these terms, okay, F4 and F3 already has some explicit parts of P outside, these are not P independent. So the ultraviolet divergence affects only the P independent parts of F1 and F2, right? Because these are the only terms that can have P independent parts. Okay, so the UV divergence will affect only these two terms. Now let's demand that S mu nu satisfies P nu S mu nu. Okay, that is the conservation of the vector current, right, without gamma phi. So that will just contract P nu with this, right? So this will give you F1 times P mu. This will be F2 times epsilon mu nu P nu. This one, P nu is P square. Okay, so this gives you P square times F3 times P mu. And this one will give you P square times F4 times epsilon mu rho P rho. This one, in fact, you can write it, but when you contract with P nu, it will give you 0 because epsilon is antisymmetric. And here you have P rho P nu, which is symmetric in rho and nu. So this will not contribute anyway. Yeah, but as I said, we shouldn't really write this as an independent tensor because it's a linear combination of these two. So if you demand that this is true, then we see that we have a relation, because comparing the coefficient of P mu, we get F1 is minus P square F3, and this is an independent tensor structure. So by comparing these, we get F2 is equal to minus P square F4. And this means that once you demand that this is true, the potentially ultraviolet divergent parts, F1 and F2, Right? These are the only ones which had no explicit P. These are determined in terms of F3 and F4, which are ultraviolet finite. So now we want to check P mu S mu nu. But with this, right, S mu nu has become ultraviolet finite. There is no further ambiguity. Okay, because once you demand that P mu S mu nu equal to 0, it's completely finite. And now whether P mu S mu nu is 0 or not has a completely unambiguous answer. If it's 0, it's well and good. If it's non-zero, you cannot attribute it to some ambiguity in the result. Okay, there is an ambiguity, of course, that we could have not demanded this, but once you demand this, then there is no ambiguity, right? And if you find that this is 0, this is non-zero, right, you have to declare that the theory is anomalous because you cannot satisfy both this and this equal to 0. Is this clear? What is the manifestation of what? Oh, because I am writing everything in terms of the tensors, right? Eta, epsilon, P, and that contraction. That's the manifestation. Yeah. Yes. This one? Yeah. Yeah. If this has log divergence, but once you demand this, right, the divergences go away. The divergent part is fixed in terms of the finite part. Exactly. Exactly. Because if F3 and F4 are finite, right? Because F3 and F4, as you can see, all had explicit P mu P, momentum factors, right? So F3 and F4 you can compute without encountering any divergence. Once you do that, then, and if you demand this, then F1 and F2 get fixed, right? And if you can pass, you can substitute it back here, and you say there is no divergence. You can, yeah, you can, but that's a unique regularization that gives you this. Right? And once you do that, then the other part is unambiguous. P mu S mu, F mu, S mu. Yes. True. Yes. So regularization will give rise to ambiguity in the answer, right? Because whenever there is ultraviolet divergence, there is you can add local terms, right? Local counter terms. But the point is that once this is demanded, then all those ambiguities go away. Right? Now, if the S mu nu is unambiguous, and now whether P mu S mu nu is 0 or not is it has an unambiguous answer. Okay. So this is just to emphasize that anomaly is due to ultraviolet divergence, but the existence of anomaly itself is not a ultraviolet regulation dependent statement. Yes.
F1 and F2, those are independent of P, right?
F1 and F2 are not necessarily independent of P, right? They are, all of these are functions of P square.
I mean, it's just the divergence.
Yeah, the divergent part is independent of P. Okay, so with this understanding, we will now start calculating this. And this calculation, okay, I have given the calculation here, but it may be hard to explain in this. Let me at least give you some details anyway. So we use the fact that, so here you have a product of gamma mu and say gamma rho, right? We use this relation that I wrote down earlier, and similarly here you have gamma nu and again gamma sigma, right? We again use this, right? Using that, we can take this product and write it. So these two factors I have written in this form, okay? And then these two factors I have written in this form. Okay? The advantage of doing this is that all the explicit gamma mu's have gone away. We only have some gamma 5s left over. And now I'm going to use the fact that trace of gamma 5 is 0. So the only way we can get some non-zero answer from here is if you pick one gamma 5 is already there. So from this product, we have to pick terms with one gamma 5, right? Because 0 gamma 5 will give you trace of gamma 5 and 3 gamma 5 will be trace of gamma 5 cube, which is the same as trace of gamma 5, and that is also 0 because gamma 5 square is 1. Okay, so you basically have to pick the product of this and this and this and this term. Okay, so that's here. And then in the next step, okay, I use what is called the Feynman parameterization. If you have, this is something a standard trick one uses. If you have 1 over f times b, it can be written as integral 0 to 1 dx times 1 over a times 1 minus x plus b times x whole square. Okay, so here these are specific quantities, but we can, if we replace this by a and this by b, there is a corresponding relation. This is an elementary integral that we can do and check that this is true. Okay, so this is a standard trick that one uses. So now, once you have written it this way, a times 1 minus x and b times x, now you just simplify this a little bit, okay, just expand this out, k minus p square, you get something like this. Okay. And now you can complete the square. Okay. You can write this as k minus xp whole square, and then you have to supply an extra x square minus x square p square. Okay, so x times p square, and there is a minus x square p square that combines into this. Okay. And I should have said this I epsilon basically is telling you how to interpret the integration over the zero component of the momentum. This is a standard Euclidean continuation. Right? This is the standard I epsilon prescription that one uses in quantum field theory. And what I'm going to do eventually, right, in this, I'm now going to reinterpret k minus xp as L. Now this again is a shift of variable, right? You may ask why, how am I allowed to shift, right? And the point is that at this stage you have only logarithmic divergent integral, right? You can see that you have 2 parts in the numerator and 2 more parts from here, right? So 4 altogether 4 parts of k in the numerator and 4 parts in the denominator. So it's logarithmically divergent. And inside logarithmically divergent integral, we can shift momentum. It's still divergent. We can regulate it, right? We can regulate it, for example, using either Pauli-Villard's or dimensional regularization. But once you regularize it, then some of these relations become not correct. In particular, suppose you dimensional regularization, continue to 2 minus epsilon dimension. The gamma 5 has no generalization to 2 minus epsilon dimension. Okay, so you have to think of the gamma 5s here as 2-dimensional gamma matrices. And with that understanding, you can try to continue this to 2 minus epsilon dimension. But then the formal proof of invariance will be lost. But as you will see, and as I have already indicated here in this, that the regularization really shouldn't affect the final result, right? Once you demand this, and we will see this. We will see that there is an ambiguity, but regularization will not affect it. Okay, are there any questions for this manipulation? Right, I am just calculating this Feynman diagram, okay, using this Feynman parameterization of the integral. Okay, so here is the expression for S mu that you got. Then, right, you have an integral over L and then integral over X. And now, in this integral, we now analytically continue from the Minkowski space to Euclidean integral. So L0 is replaced by I times LE. That's what is forced by this I epsilon, not minus I times LE, but I times LE because of this minus I epsilon. Right? You have to rotate the contour towards from minus I infinity to I infinity. And then we again use the Lorentz covariance. So if we have an integral of this kind, you see here, there is no explicit p, right? There is only p square, which is a scalar. So this integral has to be proportional to eta mu, right? And the coefficient, let's call it f. F obviously is a divergent integral because this is logarithmically divergent. Okay, so f is some divergent quantity. If we have something like this, a single L, right, there is no Lorentz invariant quantity that you can write down, Lorentz covariant quantity, so this should be 0. And you can also see that this is 0 by L goes to minus L symmetry of the integral. Okay, under L goes to minus L, the integrand just changes sign. And finally, this one is an integral that you can do, because this is just an ordinary finite integral, right? So this one, after once you continue L0 to I times LE, right, that gives an extra I, and then we define R as the square root of LE square plus L1 square. So the two-dimensional integral just becomes 2 pi R dr, and here this L square becomes R square plus x times 1 minus x, because L square, if you remember, it was minus L0 square plus L1 square, minus L0 square becomes LE square. Okay, so it's just R square plus this, and this is an elementary integral, right? Because this is the 2R dr is just d of R square. So you can easily do this calculation and you get something like this. So all of these you now substitute here. And the idea is that the L mu, L nu terms will be obtained, will be given in terms of this. Single L mu terms will vanish. And then the ones without any L, right, x times x minus 1 p mu p sigma, those will be given in using this integral. And once you do all that, right, you find that there is an expression for S mu nu like this. This is the part, okay, which is completely finite. And then there is an ambiguous part, which I have written as 4k times epsilon mu nu. This ambiguous term comes because you have this f times eta mu nu, right? And if you look at the L mu L nu term over here, there is an epsilon nu sigma times eta sigma nu. Okay, because there is an L mu L sigma, right? So epsilon nu sigma times eta mu sigma, so that gives you an epsilon times eta, f times epsilon mu nu. Another term comes because of this, L rho L nu, right? And those two terms actually cancel, they come with opposite sign. You can check because of the antisymmetry of epsilon, they come with opposite sign. But even though it comes with opposite sign, right, it's f minus f, and f is divergent. Okay? So you cannot just set it equal to 0. Right? Difference between two infinities can be anything. So you call this k. Okay? We call this 4k times epsilon mu nu. So k is ambiguous because k is of the form f times 0. Okay, it could be 0, it could be infinity, or it could be any finite number. So this is the result that we get by doing this Feynman diagram calculation, and this is the only Feynman diagram calculation that we'll be needing, okay, for most of our discussion, right? This is the only thing that we'll do, and you can see that this is a simple enough calculation that you can do easily. And now we are going to analyze what it means. Are there questions? So here is the expression again for S mu nu. Right? 2-point function of J mu and J nu written in momentum space, J mu and J nu 5. Now, let's demand P nu S mu nu equal to 0. That's the conservation of the vector current, right? Because the first index refers to the axial vector current, or J mu 5. The second index refers to the vector current, or just J nu. So let's demand P nu S mu nu equal to 0. Then when you contract with P nu, this term goes away, right? Because epsilon nu sigma, P nu P sigma. Okay, this is antisymmetric, P nu P sigma is symmetric, so this term goes away. This gives you a factor of P square times this, and this gives you 4k times epsilon mu nu P nu. So if you demand this, right, then this term 4k times epsilon mu nu P nu should cancel this term, the P square cancels, right, should cancel minus I over 2 pi epsilon mu sigma P sigma. And that fixes k to be I over 8 pi. So even though the direct calculation kept k undetermined, right, because of this ambiguity associated with ultraviolet divergence, once you demand P nu S mu nu equal to 0, k is unambiguously fixed, and S mu nu is given by this. And this is what I tried to say earlier, okay, without doing the calculation, okay, that once you demand that P nu S mu nu equal to 0, okay, then there's an ambiguity in S mu, right? It fixes S mu nu completely. Okay, and we see it here. These are expression for S mu. And now we calculate P mu S mu nu. When you calculate P mu S mu nu, this gives you minus P square, right? So that P square cancels this, so the minus I over 2 pi times epsilon nu sigma P sigma. P mu S mu nu, this gives you another term of the same kind. Sorry, this term gives you 0. P mu S mu nu, because P mu P sigma, epsilon mu sigma. Epsilon is antisymmetric, P mu P sigma is symmetric under mu sigma exchange. So this term vanishes. But this term, okay, this P square cancels this, there is I over 2 pi, and you get the same thing again, right? So that's what converts I over 2 pi into I over pi. So P mu S mu nu is given by this. And this then shows that once you demand this, we cannot also satisfy this equal to 0. Right? This is unambiguously determined to be something non-zero. And this is what is meant by the chiral current being anomalous. Okay, that you cannot preserve, we cannot have the conservation law of the vector current and the chiral current simultaneously. Now here, just note that we could have demanded that chiral current is conserved. Okay, P mu S mu nu equal to 0. Okay, so forget about this step, go back here and demand that P mu S mu nu equal to 0. That will fix K again, right? But it's the opposite side, minus I over 8 pi. And as a result, okay, S mu nu will have a different form. Okay? And now if you try to calculate the P nu S mu nu, you will get a non-zero result. Okay? So you have an option of preserving the chiral current, but violating the vector current conservation, okay? Or preserving the vector current, but violating the chiral current conservation, but not both. So the conclusion from here is that we cannot satisfy these two simultaneously. Right? One has to go. Okay, of course, you can choose to let both go. Right? If you set K equal to 0, for example, neither chiral nor vector current is conserved. Are there questions? Yes.
Is there a general? So it seems that we have to decide what we demand. In which sense is it physically more reasonable to choose one current conservation instead of the other? We might even sort of have a mixed combination.
Yeah. So at this stage, I mean, all are allowed, right? If you try to gauge some of the currents, then you have to make sure that the current that you are gauging is preserved. Right? Then the ambiguity goes away. Right? But at this stage, you can give up either one.
So you have to bring in the discussion some extra physical principles, no?
Yeah, exactly.
Okay.
Yeah.
Sorry, it's a related question. We never talk about vector current not being conserved. It's the point Benoit is making. So there are two laws that you want to demand. You could demand either regular vector you want being conserved,
Yes.
or the axial you want.
Yes.
Right? Now, there is a physical reason for why we demand the vector you want to be conserved. It's underpinnings of the standard model. So how would you answer that?
Yeah, true. In the standard model, you gauge some vector, some quantity, some symmetry, right? And then indeed it is true that the other one has to be non-conserved, right? So in a given, so here for this particular model, right, where you have not gauged anything, right, you can do either. Right? You can either have the vector current conserved or the chiral current conserved.
But once you add, let's say, electromagnetic fields, then you're forced to.
Yeah, sometimes there are, yeah, exactly. Sometimes you are forced to preserve one or the other, right?
Thanks.
When once something is gauged. Right? So that I'm going to come to that in a few minutes. Any other question? If you preserve the regularization which is vector current preserving, right, a dimensional regularization, for example, right? The vector current has no problem in getting defined because dimensional regularization, the problem is that gamma phi is ill-defined. Okay? But gamma mu is perfectly well defined, right? Can be continued in dimension. Okay? So in dimensional regularization or anything that preserves the vector gauge invariance, k will be equal to minus I over A. Okay. So at this stage, then we have three possible interpretations. Because we use three independent ingredients to arrive at this equal to 0 and this equal to 0. One is that J mu 5 is not conserved. Second is J mu is not conserved. And the third one, which is sometimes called the anomalous commutator, is that this commutator is not 0. And I'll leave it as an exercise to find the right hand side of 3 that will ensure that even though these two are conserved, these equations hold. Okay, not these equations hold, that this equation holds, right? And basically not this equation. Suppose you have chosen your regulator such that P nu S mu nu equal to 0 and P mu S mu nu is given by this. Okay? That will lead to a specific commutator that you need to achieve that. Okay, basically the idea is that when you take the del del x mu, right, and you are trying to take it inside the time order product. There is a contact term, there is a delta x0 minus x0, which involves equal time commutator. You can ascribe the failure of this relation, that fact that del mu, so what we have proved here is this one, right? That P mu S mu nu is given by this. But to go from here to del mu J mu phi, we have to make sure, we have to assume that the commutator is 0. If we allow the commutator to be non-zero, right, then you can make this compatible with del mu J mu phi equal to 0. Okay, and the exercise is to find the correct right hand side of 3 which can achieve that. Okay, and this is sometimes called the anomalous commutator. Okay, but this is, I'll not dwell too much on this aspect. So this is in some sense the elementary viewpoint of anomalies. Right? Now I'll try to develop other viewpoints. Okay, all based on the same calculation. Okay, you don't need any further calculation for at least in 1 plus 1 dimension. So let's go to viewpoint 2. So let's suppose that we couple the theory to a background gauge field, right? We are not saying at this stage that this is dynamical, it's a background gauge field via the vector current. Which means that you add a new term in the action which is given by this, okay, where E is some charge. And A nu is the background gauge field. So once you add this term in the action, right, you can, and if you try to calculate, for example, the 1-point function of J mu 5, okay, instead of the 2-point function, but in the presence of this background, you will be led to an expression like this to linear order in NU because you have e to the is, right, to the I times this, and you expand in powers of E, right, and to first order in E, you basically bring down a factor of I E times integral NU GNU. So you will get a term like this. And we see that the same correlation function has appeared here, J mu 5 J nu y, right? And we will use the S mu nu for this. So for this, let me just remind you that the definition of S mu nu was that this was the Fourier transform of this. So you can write J mu 5 J nu y as the inverse Fourier transform of S mu nu, which is here. And if you substitute it here, substitute this expression into here, we get J mu 5x in terms of S mu nu and the background gauge. Okay, and the idea is that we will now try to see what the consequence of this is. Is this okay? Any question? Right? So we are just thinking of this, now introducing a background gauge field and calculating the 1-point function of J mu in the presence of the background gauge field. Yes. Yeah, so right now we are thinking of this as some background classical gauge field, right? Eventually we would like to make this gauge field dynamical, right? This could be the standard electromagnetic field, for example, in 1 plus 1 dimension. Right now we think of this as just as some background. Okay, we have not added to the action the F mu nu term. right? And quantize nu. Just think of this as a classical diagram. Okay, so this is the expression again. Okay, and then some manipulation. So you calculate now del mu, the del x mu of j mu 5. The derivative with respect to x mu will bring down a factor of IP mu, as you can see from here. This is only x dependence. So you'll get a I times I is minus sign with a P mu S mu nu. And now we use the formula for P mu that we had used earlier here. Now earlier there's an ambiguity, okay, and the ambiguity is present here also. Okay. But the point is that if you want this to be gauge invariant, right? Imagine that you want gauge invariance under nu going to nu plus del nu theta, okay, the standard gauge invariance. Okay. Then you have no choice but to make sure that del nu j nu is 0, right? So this choice that you had made here, okay, will be forced on us, okay, if you want this one-point function to be invariant under a gauge transformation of nu. Okay, if you want that nu and nu plus del nu theta will give the same result, okay, then this is unambiguous because S mu nu becomes unambiguous and we get this expression over here. Now a little further manipulation, we can write this I p sigma as del x sigma of this, right? Because again the x dependence is only here. So this is del x sigma, and then minus sign cancels e over pi, and so we get del x sigma. Now the integral of p, once this is gone, integral of p just gives you delta x minus y, delta to x minus y. The y integral can be done. So we get e over pi epsilon nu sigma del x sigma a nu, and then we use the fact that this is already antisymmetric in nu and sigma. So we can write this in terms of the gauge field strength, F nu sigma. Right? F nu sigma is basically del nu a sigma minus del sigma n. Okay? This minus sign comes because it's in the opposite order, right? This is del sigma a nu, right? Whereas F nu sigma is normally defined as del nu a sigma. And the 2 comes because here there's only one term, you have to antisymmetrize, and that gives a factor of 2. So this means that if we are working in quantum electrodynamics, suppose the mu was a dynamical gauge field, then you have no choice but to ensure that nu gauge invariance is preserved. And once you demand that nu gauge invariance is preserved, nu going to nu plus del nu lambda, del nu theta is a symmetry, then this you cannot avoid, right? You have to demand this, right? Otherwise this will not have that symmetry. J mu 5x will not have that symmetry. So this is forced on us by gauge invariance of the theory, and as a result we see that J mu 5 is not constant. So this leads to the conclusion that in quantum electrodynamics, the chiral current is not conserved in the presence of a background gauge field. Okay, it's given by this expression over here. Yes. This to this. Well, I just applied del x mu on this object. Sorry, what did I do here? Okay. Yeah. Second to third line, I use P mu S mu nu. S mu nu is the same calculation that we had done earlier, right? So P mu S mu nu we had seen earlier is minus I over pi epsilon nu sigma P sigma. Right? Provided you demand that P nu S mu nu equal to 0. And what I'm saying is that P nu S mu nu equal to 0 is a consequence of the gauge invariance associated with nu. Right? If you start from here and if you demand that nu going to nu plus del nu theta is a symmetry, gives the same result, then we can do integration by parts and you arrive at the result that P nu S mu nu equal to 0. Yeah, so when we had just the currents, no gauge fields, you had a choice. Right? But if there is a background, if there is a gauge field that is coupling to the system, right, then you want to maintain gauge invariance. Right? Particularly if you eventually want to make that gauge field dynamical. Right? So there, nu going to nu plus del nu theta has to be imposed explicitly. Yeah, so if it's a background, you can say, okay, we don't care, we don't need gauge invariance, right? In which case, again, we'll have an ambiguity. But once nu, if you want to make nu actually as a quantum field, right, and you quantize it, then you need a gauge invariance for consistent quantization of the theory. And there, nu has to be conserved. Is this okay? Are there questions? So this shows that mu5 is not conserved. Now, it is true that even though mu5 is not conserved, we can actually add to mu5 a local term involving gauge fields, which I have given here, which makes it conserved, right? In fact, del mu j hat mu5, right? You can calculate, and this for this you use the formula that you have gotten here, and for this you calculate it explicitly, which is here, and these two, in fact, do cancel. Okay, in fact, this was designed to cancel that. So it is possible to define a conserved current, conserved chiral current, by adding something to it, but this something that we add is not gauge invariant, right? Because under a sigma going to a sigma plus del nu theta, it's not zero, this quantity. Okay. So this is again a general lesson, okay? May not be always true, but it is true in here as well as in 3+1 dimension in abelian theories, that even though the chiral current is not conserved, we can add to it a local expression, which makes it conserved, but the price you pay is that that quantity is not gauge invariant. Okay, and we see this explicitly here, that this quantity is not gauge invariant. Are there questions? Yeah, some people do make use of this, right? So this says that for some purpose you can have a conserved current, but not for all purpose, right? So I mean, when this gauge invariance problem is not serious, right? Then you can make use of this, right? Yeah, it's some that you have to make a gauge choice. I mean, the question is, for some cases, this even though you are adding this, it doesn't do anything. Right? So for that, you can have a conserved current, right? Which even though it's not gauge invariant, but in general, you cannot trust the chiral current conservation. Yes.
So one question is related to what happens if you expand in higher order the response to the U1 gauge field, because you base your calculation, I think, on linear response. Yeah. In principle, you could have some non-linear terms. And okay, I'm not an expert in anomalies, but I believe that there's some of folklore, maybe not folklore, something very deep that tells you that all non-linear terms in the response sort of vanish in this situation.
Yeah, at least they are all gauge invariant. One can show that because if the nonlinear terms, once you insert more amus, right, it's like you have a loop with 3 insertions, and exactly. That's UV finite. And those don't give rise to any anomalies. So the nonlinear terms, there can be, of course, other terms, but they all give gauge invariant result.
Okay.
Okay. So the gauge non-invariance comes only from the anomaly, the 2-point function.
But the existence of the anomaly, does it imply something for the possible vanishing of these higher order corrections, or?
Not necessarily, because you could have extra term, for example, f mu to the 4, trace, say f mu to the 4, right, with appropriately contracted indices. That is gauge invariant. Okay. So the anomaly by itself doesn't prevent that term.
Okay.
Right? There may be other arguments which you can use, but not anomaly itself.
Okay, thank you.
Yes. Pardon? Yeah, that you see that this is not conserved. because this is a linear response, and we have worked out the first order in a linear term in any. Well, we can think of this as an expansion in E or an expansion in A. Right? Now, because we are considering only 2-point function. Right? If you look at this expansion, there are also E squared times 2A's J mu, J nu, J nu. Right? So those terms here we have not considered because they are all UV finite and they don't contribute to anomalies. Okay, so let me now then describe the third viewpoint, okay, which is not very different from what we had earlier. And that will be to couple both J mu and J mu 5 to background gauge fields. So you add a term in the action, which is A mu J mu and B mu J mu 5. And here I have just dropped the E's, right, because I have absorbed them inside A mu and B mu, right, just for convenience. Later on, we'll bring back the E's at some point. Now to quadratic order, okay, the fermion loop basically generates new contribution to the effective action of A mu and B mu. And this will now involve these factors you can work out, right, by using standard perturbation theory. So there are terms like A mu, A nu, J mu, J nu, right, when you take the square of this, you bring 2 powers of this. Then B mu, B nu, J mu 5, J nu 5, when you bring 2 powers of this, and then there is a cross term with A mu and B mu, which is given here. Now we can go to the Fourier space. So A mu we write in terms of the Fourier transform variable, B mu we write in terms of Fourier transform variable, okay. And then this quantity, right, I can rewrite in the Fourier space, and it's the same S mu nu that appears here because this is S mu nu is the Fourier transform of J mu 5 with J nu y. Okay, so this term you can calculate in terms of the S mu nu that we had already computed earlier. Okay, so let me remind you again that what we are calculating is an effective action involving the external gauge fields, B A and B. Any question on this? So similarly, we can calculate the A mu nu term, and we can write in the Fourier space R mu nu, okay, where R mu nu is defined exactly in the same way as S mu nu, except that here instead of J mu 5 and J nu, I have both J mu and J nu. Okay, that's the only difference. And similarly, this one I can write in terms of Q mu nu, okay, where in Q mu nu I have both J mu 5 instead of one J mu 5 and one J nu. Now, we can calculate these objects R mu nu and Q mu nu using similar method as S mu nu, right? Basically, what will happen is that one of the gamma 5s are either missing or there are 2 gamma 5s instead of one gamma 5 and one gamma 5 gamma mu and one gamma nu. But we can also use these relations that we had found earlier, right? The gamma matrix relations, the J mu 5 is given by this, and you can invert this to write J mu as a linear combination of J 5. And using this, we can relate Q and R to S, right? Because S had a J mu J nu, sorry, J mu 5 J nu. Okay, so you can, if you want to J mu, right, you just write the J mu in terms of a linear combination of J mu 5 using the epsilon. So you can use this relation to calculate the corresponding quantities R and Q. But one important point here is that we can do this for ultraviolet safe terms. We cannot use this relation for the ultraviolet divergent terms because with infinity you cannot manipulate. Okay, so you have to keep the ultraviolet divergent terms arbitrary. Okay. For example, if you do dimensional regularization, then this relation is not valid in arbitrary dimension, right? Because epsilon is not even defined in arbitrary dimension. Okay, so this is something we should keep in mind. So UV divergent terms, we have to still allow for arbitrary coefficients. So with this understanding, we get, so this was the original expression for S mu nu that we had found. For R mu nu and Q mu nu, we have these new expressions and new constants have appeared here. These are the constants that are coefficients of the ultraviolet divergent terms. Okay, so we leave them unchanged, we leave them unfixed at this stage. So this is what I have said, that these are arbitrary constant, ultraviolet sensitive, and these can be changed by what we call local counter terms, right? Because these are essentially terms in which involve, say, A mu A nu or B mu B nu or A mu B nu, right? These terms can be changed. So here is the expression for the effective action again, right? The same expression that we wrote here, this one. And now we want to see what happens under a gauge transformation of A mu and B mu. So introduce two independent gauge parameters. One is theta that transforms A mu, and the other one is phi, which transforms B mu. So these are the standard abelian gauge transformation laws of these gauge fields, and the corresponding momentum space version is given here. Okay, the derivatives basically become I times B. And now it's just straightforward, right? You have this W and you transform it. You transform it, okay, there are some symmetries that you can use because R mu nu is, for example, symmetric and mu and nu. So some terms can be simplified. But at the end, what you get for delta W, okay, the change in this under a gauge transformation is written here. Okay, it's a straightforward exercise, but you can see this. Is this okay? Are there questions? Here is again the same expression. And now you see that by looking at this, that it's impossible to make a choice of K, L, and M that make this vanish. The best you can do is to make these terms vanish. L and M you can set equal to 0. And then we can either make this vanish or this vanish. Both of these cannot vanish because you see that there is a minus I over 2 pi plus 4k and minus I over 2 pi minus 4k. So we cannot make both of these vanish. And this says that if we try to couple the system to two gauge fields, one coupling to vector current and one coupling to chiral current, you cannot maintain both gauge invariances at the same time. Okay, you can either maintain chiral invariance or vector invariance, but not both. So you can make only one of the two gauge fields dynamical. Okay, because once you make it dynamical, gauge invariance is better be preserved. So this viewpoint tells us that there is an obstruction to gauging these symmetries. Right? You cannot gauge both vector and chiral gauge symmetries at the same time. Yes.
The violation of current conservation, what does the right-hand side look like for two gauge fields?
What does the right-hand side look like?
Presumably both the chiral and vector and axial vector currents are not conserved in the presence of both A and B.
In the presence of, well, no, you can make the vector current conserved or axial vector current by choosing K appropriately. Right? So, yeah, so you can still maintain one current conserved, right? So you can gauge one of the gauge. You can make one of the gauge fields dynamical, right? Because that gauge invariance you can preserve.
But if I choose to just leave K unfixed,
then another gauge invariance is
but what
K unfixed meaning you have to fix a K, right? To do any calculation, you better fix a K, right? For any amplitude, this diagram is going to appear as sub-diagrams of various amplitudes, right? So you have to fix a K, right? And once you fix a K, then that determines which one you can gauge.
Because I think when we preserve vector symmetry,
Yes.
the del mu J mu 5 is violated by some topological term. Right?
Yes, that's this. That's basically this. That you already saw in the earlier one. That's the same expression. Yeah, this one.
So I was just wondering if you keep K, it just the right hand side just has K appearing in it.
Yeah, it will have a K appearing, but then the price you pay is that then the vector current also has an anomaly. right, which is proportional to the chiral gauge speed. Yes.
Constraints on the choice of B mu, because now B mu is different because it couples to J mu 5, which violates parity.
Yes.
So does it constrain the choices of B mu, or these are not allowed in some cases?
That depends on the physics of the problem, right? Just as a quantum field theory, you can certainly have a system where B mu couples to this, right? As long as there's no mu, right? If mu is 0, then there is a confusion, there is an obstruction to having B mu coupling to the system. Any other question? Yes.
What is the difference in the transport when it is current and the axial current and the
Well, J mu 5 expectation value you can think of as, well, I don't know if it's transport. Transport is a response. Yeah. So so this is like a transport, right? We switch on, for example, the background vector current, and then you find that the corresponding current is not constant, right? So you are basically losing some charge in the background. Right? So that's the closest thing I can think of as connecting this to transport, right? Because the transport has dissipation, right? Because the current is not constant. Yes. Yeah. Reference to for anomalies. Okay, I'll send all the reference. Yeah. Okay. Okay. I think my time is almost up. Okay. Yeah. So maybe let's see what is there next. Yeah. Okay. So next one will be the fourth viewpoint, which I'll discuss next time. Okay, where you really think of as a chiral current, a chiral theory, not a theory which has both left and right-handed fermions, and then couple it to a gauge field, and we'll see what happens. Okay, so I think I'll stop here.
So these are all the statements for 2D. So how many of them can be generalized to 4D? Or
Most of them we will discuss 4D next time.
Okay.
Right? And we will say that most of this will hold also in 4D.
Well, properties of 2D, they are important to make these proofs.
Yeah, but there are similar properties in 4D. Right? I mean, this, for example, will not hold this fact that the vector current correlation functions can be calculated from the chiral current ones, right, or vice versa. This will not be true, but you can explicitly calculate it, right? For it will be a 3-part function. Okay, but otherwise, most of the general principles will go over to 4D also.
If there are questions online, you can unmute yourself and ask the question now. Oh, okay. So, sure. Yeah.
Could you possibly give connection to how the chiral anomaly is usually presented in QFT books? So if you follow sort of the Adler-Bell-Jakiev, write down the triangular diagram and you argue that diagram gives you sort of the anomaly and it's related to, let's say, pion production. How do I see it from this language? I realized here
so
it's a toy model, but still, is there some way for you to connect the triangular diagram?
Yeah, so this in 1+1 dimension is that not the triangle diagram that is relevant, it's a 2-point function. Exact analog of this in 3+1 dimension will be the triangle diagram.
Oh, and And can I see why in 4 dimensions I need 3 vertices and here it's enough to have 2?
It's possible to see, I'm sure. Okay, I mean, I'll try to think of a proper answer. I can't see it immediately, right? That, I mean, in 2 dimension, triangle diagram is not important because it's UV finite. Right? In 4 dimension, triangle diagram is UV divergent, right? But so is this one, right? I mean, the question is, why isn't the bubble diagram important in 4 dimensions? Right? That's I think the relevant question, and I'll try to think about this the answer to this.
Thank you.
Yeah, maybe I can say roughly, but I have to think about this. That in 4 dimensions, what happens? We have one gamma phi in this whole loop, right? And many gamma mu's. In 2 dimensions, you use the fact that this gamma mu can be written in terms of the gamma phi plus something. I think in 4 dimensions, the analog of that will be 3 gammas. And I think that's what makes it that if you have a single gamma phi, right, you don't get anything non-trivial. But I'll try to work this out and try to answer tomorrow.